Ensuring nuclear arsenal reliability, the science and strategies of non-detonative testing. The challenge of maintaining a reliable nuclear arsenal without conducting live detonations is one of the most complex and critical tasks faced by the United States defense establishment. This intricate process involves cutting-edge technology, advanced scientific methods, and a deep understanding of both physics and engineering. Here, we delve into the multifaceted approach employed by the U.S. to ensure its nuclear weapons remain functional and effective as deterrents without resorting to actual nuclear tests. Historical context and the need for non-detonative testing. From the inception of nuclear weapons in the mid-20th century until the early 1990s, the United States conducted over 1,000 nuclear tests. These tests provided invaluable data on the behavior and performance of nuclear weapons, which in turn informed the design and maintenance of the nuclear stockpile. However, the environmental, political, and ethical implications of nuclear testing led to a global push for comprehensive test bans. The culmination of this effort was the Comprehensive Nuclear Test Ban Treaty, CTBT, which, although not fully ratified by all nuclear powers, has led to a de facto moratorium on nuclear testing since 1992. In this context, ensuring the reliability and safety of nuclear weapons without live testing became paramount. The United States responded with the Stockpile Stewardship Program, SSP, a sophisticated framework designed to maintain the nation's nuclear arsenal through advanced scientific and technological methods. The components of the Stockpile Stewardship Program. The SSP relies on three main pillars: theoretical models, simulations, and experimental data. Each of these components plays a crucial role in understanding and predicting the behavior of nuclear weapons under various conditions. 1. Theoretical models. The foundation of the SSP is built on theoretical models that describe the physical principles governing nuclear reactions and material behavior. These models are based on decades of research and empirical data from past nuclear tests. Theoretical models help scientists understand the underlying mechanics of nuclear explosions, from the initial detonation to the subsequent chain reactions and energy release. 2. Advanced simulations. Theoretical models alone are insufficient to ensure the reliability of nuclear weapons. To complement these models, the SSP employs advanced simulations run on some of the world's most powerful supercomputers. These simulations are designed to replicate the conditions and processes of a nuclear explosion in a virtual environment. Supercomputers and simulation software Trinity and Sierra. The Los Alamos National Laboratory operates the Trinity supercomputer, while the Livermore National Laboratory runs the Sierra supercomputer. These machines rank among the top in computational power globally and are specifically designed to handle the complex calculations required for nuclear simulations. Simulation software. The software used in these simulations is tailored to model every aspect of a nuclear weapon's performance. This includes the behavior of materials under extreme conditions, the interactions between different components, and the effects of external factors such as temperature and pressure. Simulation scenarios. Simulations cover a wide range of scenarios to ensure comprehensive understanding and preparedness. These include aging and degradation. Over time, the materials and components of nuclear weapons degrade. Simulations help predict how these changes affect weapon performance and identify potential points of failure. Environmental stress. Simulations model how nuclear weapons would behave under various environmental conditions, such as high temperatures, humidity, and mechanical stress. Countermeasure resistance. Understanding how nuclear weapons would perform against modern countermeasures and missile defense systems is critical. Simulations help assess the resilience of weapons to these challenges. 3. Experimental data. While simulations and theoretical models provide significant insights, they are not sufficient on their own. Real-world experimental data is crucial for validating and refining these models. The SSP incorporates several types of experiments to gather this data. National Ignition Facility, NIF. The NIF, located at Livermore National Laboratory, is home to the world's most powerful laser. This facility uses 192 laser beams to heat and compress small targets to conditions similar to those found in nuclear explosions. Material testing. By heating materials to millions of degrees, scientists can study their behavior under extreme conditions. This data helps improve the accuracy of simulations and models. Fusion experiments. NIF also conducts experiments on nuclear fusion, the process that powers the sun and hydrogen bombs. These experiments provide insights into the fusion reactions that occur in thermonuclear weapons. Z-Machine. The Z-Machine, operated by Sandia National Laboratories, is another key experimental facility. It generates extremely powerful electrical pulses to study material behavior and nuclear fusion. High-energy pulses. The Z-Machine can produce conditions similar to those in a nuclear explosion, allowing scientists to observe how materials and components react. Fusion research. Like the NIF, the Z-Machine is used to study nuclear fusion, contributing to the understanding of thermonuclear weapon behavior. Non-nuclear explosive testing. In addition to laser and electrical pulse experiments, the SSP conducts non-nuclear explosive tests. These tests involve the detonation of conventional explosives to study the behavior of nuclear weapon components. High explosive experiments. These experiments use conventional explosives to simulate the initial stages of a nuclear explosion. They provide data on how the weapon's components respond to shock and pressure. Centrifuge tests. Components are subjected to high rotational speeds to simulate the forces experienced during a missile's re-entry into the atmosphere. This helps ensure that all parts of the weapon can withstand the stresses of deployment. Big explosives. Experimental facility, BEEF. BEEF, located in Nevada, is another critical site for experimental data collection. Here, large-scale experiments are conducted to study the behavior of non-nuclear components of nuclear weapons. Structural testing. These tests involve the detonation of conventional explosives to study how the structural parts of a nuclear weapon hold up under extreme conditions. Component response. BEEF experiments help determine how various components of a nuclear weapon respond to different types of stress and damage. Integrating data for comprehensive understanding. The data gathered from simulations, theoretical models, and experimental tests are integrated to create a comprehensive understanding of the nuclear stockpile. This integrated approach ensures that the U.S. can maintain a reliable and effective nuclear arsenal without conducting live tests. Model validation. Experimental data is used to validate and refine theoretical models and simulations. This iterative process improves the accuracy and reliability of predictions. Continuous improvement. The SSP is an ongoing effort, with continuous advancements in technology and science contributing to a deeper understanding of nuclear weapons. The role of deterrence. The ultimate goal of the SSP is to maintain a credible nuclear deterrent. In the realm of international relations, deterrence is the strategy of preventing adversaries from taking hostile actions by ensuring they face unacceptable consequences. A reliable nuclear arsenal is a cornerstone of this strategy. Perception of capability. For deterrence to be effective, adversaries must believe that the U.S. nuclear arsenal is fully functional and capable of delivering devastating responses. The SSP ensures this perception is based on reality. Preventing nuclear conflict. By maintaining a credible deterrent, the SSP helps prevent nuclear conflict. Adversaries are less likely to consider a nuclear attack if they believe the U.S. can retaliate effectively. Ethical and political considerations. The SSP operates within a complex ethical and political landscape. The cessation of live nuclear testing reflects a commitment to global disarmament and non-proliferation, but it also poses challenges for maintaining a credible deterrent. International treaties. The CTBT and other treaties reflect a global consensus against nuclear testing. The SSP demonstrates that it is possible to maintain nuclear security without violating these agreements. Public perception. Maintaining transparency and public trust is crucial. The SSP must balance the need for secrecy in national security with the public's right to understand how their safety is ensured. Future directions and challenges. As technology and international dynamics evolve, the SSP will face new challenges and opportunities. Ongoing research and development will be essential to address these changes. Advancements in technology. Continued advancements in computational power, materials science, and experimental methods will enhance the SSP's capabilities. Global security dynamics. Changes in international relations and the emergence of new nuclear powers will influence the strategies and priorities of the SSP. Conclusion. The United States' approach to maintaining a reliable nuclear arsenal without live testing is a testament to the power of science and technology. Through a combination of theoretical models, advanced simulations, and rigorous experimental data, the Stockpile Stewardship Program ensures that the nation's nuclear weapons remain a credible deterrent in a complex and evolving global landscape. This intricate and multifaceted strategy not only upholds national security, but also contributes to global efforts towards nuclear disarmament and non-proliferation.